Tonight we're going to explore one of the strangest predictions in all of particle physics. Somewhere in the subatomic world, there may exist a particle that contains no ordinary matter whatsoever. No quarks, no electrons, nothing you'd recognize as a building block of the stuff around you. Instead, this particle would be made entirely from the force that holds atomic nuclei together. The glue itself, bound to nothing but more glue. Physicists call it a glueball. And if that sounds impossible, if it sounds like saying you could build a wall out of pure gravity or weave a rope from raw magnetism, that's because this idea challenges everything you think you know about what particles are and what forces do. For over 4 decades, the math has demanded glueballs must exist, but finding one has been one of the hardest challenges in modern physics. After all that searching, scientists may have finally caught a glimpse. Before we go any further, if you find these kinds of deep explorations into the stranger side of physics interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Everything you've ever touched, everything you've ever seen, every atom in your body, and every star in the sky is built from a surprisingly short list of ingredients. Take apart any piece of matter far enough, and you'll find just 2 types of particles doing all the heavy lifting. Quarks, which cluster together in groups of 3 to form the cores of atoms, and leptons, which include the electron, the tiny charged particle that orbits those cores and makes chemistry possible. That's it. Every element on the periodic table, every molecule, every cell, every planet, all of it traces back to quarks and leptons arranged in different combinations. For decades, physicists have been cataloguing the particles they find in collider experiments and in cosmic rays, and every single confirmed particle fits neatly into this framework. Every single one is either made of quarks, made of leptons, or is one of the force carriers that lets quarks and leptons interact with each other. Except, possibly, one. There may exist a particle that contains no quarks at all, no electrons, no leptons of any kind, nothing you'd recognize as a building block of matter. Instead, this particle would be assembled entirely from the carriers of a force. Not the matter that feels the force itself, tangled up and bound into a knot of pure interaction. This is the glueball, and if it exists, it would be unlike anything else in the known catalogue of particles. To understand why physicists think such a thing is even possible, and why it has taken more than 4 decades to track one down, you need to understand something peculiar about the force that holds atomic nuclei together, something that sets it apart from every other force in nature. But first, let's talk about forces themselves, because the story of the glueball begins with a question that sounds almost childish in its simplicity. What actually happens when 2 particles interact? When you push a door open, it feels like direct contact. Your hand touches the door, you apply pressure, the door swings. Simple. But at the atomic level, nothing actually touches anything. The atoms in your hand never make contact with the atoms in the door. What happens instead is that the electrons on the surface of your hand repel the electrons on the surface of the door through the electromagnetic force. There's always a gap, always a force acting across space. And this raises a deep question that troubled physicists for centuries. How does the force get from one particle to another? How does an electron over here know there's another electron over there that it should push away from? In the early 1900s, physicists grappled with this problem seriously. The old idea, going back to Michael Faraday in the 1800s, was that forces act through invisible fields stretching across space. An electron creates an electric field around itself, and another electron entering that field feels a push. This works well enough for many calculations, but quantum mechanics, which was being developed in the 1920s and 30s, revealed something more specific and more strange. Forces aren't just abstract fields filling empty space, they're carried by particles. This is one of the most important ideas in modern physics, and it's worth spending a moment to really understand it. Every fundamental force in nature operates by exchanging particles between the objects it affects. These exchange particles are called force carriers, or gauge bosons, and the way they work is beautifully strange. When two electrons repel each other, what's actually happening at the quantum level is that they're exchanging photons between them. Not real photons, not the kind you can see with your eyes or detect with a camera. These are virtual photons, quantum objects that exist only during the brief instant of the interaction, popping into existence just long enough to carry the force's message from one electron to the other, before vanishing again. The electron doesn't know about the other electron in some mystical way. It knows about it because it keeps receiving these virtual photons, these tiny quantum messengers that carry information about the other particle's presence and charge. This might sound like an abstract mathematical trick, something physicists dreamed up to make their equations neater, but it's not. This framework, called quantum field theory, is the most precisely tested theory in the history of science. Its predictions match experimental measurements to more than 10 decimal places in some cases. No other theory in any field of science has ever achieved that level of agreement with observation. Every technological application of electromagnetism, from the screen you're watching this on, to the satellites orbiting Earth, to the MRI machines in hospitals, operates in a universe that works exactly the way quantum field theory says it does. The virtual photon picture isn't a metaphor. It's the closest description we have of what reality actually does. So the electromagnetic force is carried by photons. The weak nuclear force, which governs certain types of radioactive decay, is carried by three heavy particles called the W+, the W-, and the Z boson. Gravity, if it follows the same pattern, would be carried by a hypothetical particle called the graviton, though we haven't detected one yet. And the strong nuclear force, the one that matters most for our story tonight, is carried by particles called gluons. Now here's where things get deeply interesting, and to see why, you need to understand one specific property of photons, something so simple it almost seems trivial. But it turns out to be the single most important difference between electromagnetism and the strong force. It's the difference that makes glueballs possible, and without it, the rest of this story couldn't exist. Photons do not carry electric charge. Think carefully about what that means. The electromagnetic force is all about electric charge. Positive charges attract negative charges. Like charges repel each other. The entire force exists because of charge. But the photon, the particle that carries this force, is itself electrically neutral. It has zero charge. This means photons don't feel the electromagnetic force the way charged particles do. A photon can carry the force's message from one charged particle to another, but it doesn't interact with other photons in the same way. Two photons can pass right through each other without any electromagnetic interaction between them. You can shine two flashlights so their beams cross in mid-air, and the photons in one beam sail past the photons in the other beam as if they weren't there. Each photon is oblivious to every other photon, at least as far as the electromagnetic force is concerned. This is a crucial detail. Because the force carrier doesn't carry the charge of its own force, the electromagnetic force has a relatively simple mathematical structure. Photons are messengers, and they're neutral messengers. They deliver the message without getting tangled up in the drama themselves. They do their job and they move on. Now let's turn to the strong force. And this is where the universe gets genuinely weird. The strong force is the most powerful force in nature. It's roughly 100 times stronger than the electromagnetic force at the distances where it matters most, deep inside the atomic nucleus. It has to be that strong because it has an incredibly difficult job. Think about what's happening inside the nucleus of an atom. Protons are packed together in an incredibly small space, and protons are positively charged. They should repel each other with enormous electromagnetic force. Every proton in the nucleus is screaming at every other proton to get away from it. And yet, the nucleus holds together. Atoms exist. Matter is stable. The strong force overpowers the electromagnetic repulsion and binds protons and neutrons into a stable core that can endure for billions of years. But the strong force doesn't act on electric charge, it acts on a completely different kind of charge. A kind of charge that most people have never heard of. Physicists call it color charge. Now, immediately, let me be very clear about something. Color charge has absolutely nothing to do with actual colors. Protons are not literally red. Neutrons are not literally blue. Quarks aren't painted. The name is a metaphor, an analogy physicists adopted in the 1960s because it happened to map conveniently onto the mathematics. There are 3 types of color charge, and physicists needed short labels for them, so they borrowed the 3 primary colors of light: red, green, and blue. They could have called them Type A, Type B, and Type C. They could have called them vanilla, chocolate, and strawberry. The physics would be identical. But the color names stuck, and so that's what everyone uses. What matters is that color charge is a real physical property, just as real and just as fundamental as electric charge. Quarks carry color charge. Every quark has one of 3 color charges at any given moment: red, green, or blue. And there are also anticolors: anti-red, anti-green, and anti-blue, carried by antiquarks. And just as the electromagnetic force acts between electrically charged particles, pulling opposite charges together and pushing like charges apart, the strong force acts between particles that carry color charge. Any particle carrying color charge feels the strong force. Any particle without color charge does not. Now here's the critical moment. The punchline of everything we've been building toward. The fact that changes everything about how the strong force behaves. Gluons carry color charge. Unlike photons, which are electrically neutral and don't carry the charge of the force they transmit, gluons carry the very charge they're supposed to be mediating. Each gluon carries a combination of a color and an anticolor, not just one label, but 2, mixed together in a specific quantum mechanical way. And because there are 3 colors and 3 anticolors, you might expect 9 possible gluon types. But due to the specific mathematical symmetry governing the strong force, one of those 9 combinations cancels itself out, leaving 8 distinct types of gluons. Each one carries its own particular mix of color and anticolor charges. This might sound like a minor technical footnote, a detail for textbooks. It's not. It's the most important fact in this entire story. It's the reason glueballs are even conceivable. And here is why. Because gluons carry color charge, they feel the strong force. They don't just transmit the force between quarks, they experience it themselves. They are both the messenger and the audience. When one gluon travels between 2 quarks to deliver the strong force's message, it can interact with another gluon along the way. It can attract other gluons. It can emit entirely new gluons. It can absorb gluons coming from other directions. The messenger is not neutral. The messenger is deeply, fundamentally part of the conversation. Imagine a postal service delivering packages between houses. In the case of electromagnetism, the postal workers are invisible to each other. They do their jobs, deliver their packages, and pass right by one another without any interaction. Each one is independent. But in the case of the strong force, the postal workers are not invisible to each other. They shout at each other. They grab each other's arms. They form clusters. Sometimes they get so tangled up with each other that they forget about the houses entirely and form their own little group, passing packages among themselves in a closed loop that has nothing to do with the quarks they were supposed to be serving. That closed loop, that self-contained knot of interacting gluons, is what a glueball would be. Let's appreciate just how radical this is. In every other force we understand well, the force carrier is a passive vehicle. It goes from point A to point B and delivers the interaction. The carrier doesn't generate more carriers on its own. The carrier doesn't tangle itself into knots. The carrier doesn't form independent structures. But the strong force is different. Its carriers are active participants. They are sources of the very field they carry. And this single property, gluon self-interaction, creates a cascade of consequences that make the strong force behave in ways that are completely unlike anything else in physics. To understand how deep this difference goes, consider what happens when you separate two electrically charged particles. Imagine pulling a positive charge away from a negative charge. As they move apart, the electromagnetic force between them weakens. It drops off smoothly with distance, following the familiar inverse square law. Double the distance, the force drops to a quarter of what it was. Triple the distance, it drops to a ninth. Move them far enough apart, and the force becomes negligible. The particles barely notice each other. The electric field lines spread out in all directions through space, thinning as they go, like water fanning out from a sprinkler. This is intuitive. This is what you'd expect. And this is why atoms can exist as electrically neutral objects. The positive and negative charges balance, and at any appreciable distance, the net electromagnetic field is essentially zero. Now try the same thought experiment with quarks. Pull two quarks apart, and at first, the strong force between them behaves somewhat like you'd expect. There's a powerful attraction, mediated by gluons streaming back and forth. But as you increase the distance, something bizarre happens. The force doesn't weaken. Instead of spreading out in all directions like electromagnetic field lines, the gluon field lines bunch together. They squeeze into a narrow tube, a string of concentrated force energy connecting the two quarks. And as you pull the quarks farther apart, this tube doesn't thin out. It stretches, but it stays dense. The energy stored in the tube keeps increasing with distance. The farther apart you drag the quarks, the more energy you pour into the system. Why does this happen? Because gluons interact with each other. In electromagnetism, field lines spread freely because photons don't attract each other. They have no reason to cluster together. But gluon field lines are different. Because gluons carry color charge, the field lines themselves are sources of more field. They attract each other, pulling together into a narrow bundle instead of spreading out. This self-attraction of the gluon field is what creates the flux tube. It's somewhat like stretching a rubber band. The farther you pull, the more energy you store, and the harder it snaps back. This leads to an astonishing consequence. If you try to pull a quark completely free, if you try to isolate a single quark from all other quarks, the energy stored in the stretching flux tube eventually becomes so enormous that something dramatic happens. The tube snaps. But it doesn't release a free quark on either end. Instead, the energy in the snapping tube converts into matter, specifically a brand new pair of particles, a quark and an antiquark, which immediately bind to the original quarks. You started with two quarks connected by a gluon tube. You tried to rip them apart. The tube stretched, stored energy, and then snapped, creating new quarks that recombined with the originals into two new bound pairs. You ended up with more particles than you started with, but still no free quarks. The strong force simply will not let go. This phenomenon is called confinement. Color-charged particles can never be observed in isolation. You can never hold a single quark in your hand. You can never put one in a box by itself. You can never photograph one sitting alone. Every quark in the universe is locked up inside a larger composite particle, bound to other quarks by gluons that absolutely refuse to release their grip. Confinement isn't just a practical limitation, like saying you can't see a quark because it's too small. It's a fundamental law of nature. The strong force literally will not permit a color-charged particle to exist on its own. The universe enforces this rule with absolute and unyielding authority. And what enforces this rule? Gluon self-interaction. If gluons didn't carry color charge, the gluon field lines would spread out just like electromagnetic field lines. The force would weaken with distance, and eventually quarks could be separated. But because gluons pull on each other, the field lines stay bundled, the force stays strong, the flux tube forms, and quarks stay permanently confined. Every aspect of confinement traces back to that single property. Gluons carry the charge of their own force. Now, there's another consequence of gluon self-interaction that seems to contradict everything I just told you, and it's equally important. When quarks are very close together, much closer than the width of a proton, the strong force actually becomes weaker. The closer two quarks get to each other, the less they pull on each other. At extremely short distances, quarks behave almost as if they're free particles, barely interacting at all, drifting past each other like strangers on a sidewalk. This is called asymptotic freedom, and it's one of the most counterintuitive discoveries in the history of physics. A force that gets stronger as you move apart and weaker as you move closer. That's the exact opposite of electromagnetism, where the force grows stronger as charges approach each other. It's the opposite of gravity. It's the opposite of your everyday experience with almost everything. How can the same force be incredibly powerful at the distance scales inside a nucleus and essentially negligible at even shorter distances? Once again, the answer is gluon self-interaction. At very short distances, the gluons surrounding a quark create a complex cloud of virtual gluon pairs and quark-antiquark fluctuations. This cloud has a remarkable effect on the color charge. Virtual quark-antiquark pairs partially screen it, much as virtual particle pairs screen electric charge in electromagnetism. But the virtual gluons do something completely different. Because they carry color charge themselves, they anti-screen, amplifying the effective charge and spreading it outward. At larger distances, this amplification makes the color charge appear enormous, producing the powerful binding that confines quarks. But at very short distances, before the amplification has built up, the effective charge is small and quarks barely interact. This effect is uniquely driven by gluon self-interaction. It cannot happen in electromagnetism because photons don't interact with each other. The discovery of asymptotic freedom in 1973 was a genuine breakthrough. David Gross, David Politzer, and Frank Wilczek showed mathematically that the strong force weakens at short distances, and the result earned them the Nobel Prize. It was also the moment when the theory of the strong force, called quantum chromodynamics, became a serious, predictive, quantitative framework for understanding what happens inside protons and neutrons. Before 1973, physicists knew the strong force existed. They knew it held nuclei together. Murray Gell-Mann and George Zweig had independently proposed the quark model in 1964, suggesting that protons and neutrons were made of smaller constituents. And experiments at the Stanford Linear Accelerator Center in 1969 had fired high-energy electrons deep into protons and found evidence of hard, point-like objects rattling around inside, just as Rutherford had fired alpha particles at gold foil decades earlier and discovered the atomic nucleus. But understanding the precise force that bound those quarks together had remained elusive until quantum chromodynamics came together as a complete theory. And the key to quantum chromodynamics, the feature that distinguishes it from every other force theory in physics, is gluon self-interaction. Every distinctive property of the strong force flows from this one source. Confinement, asymptotic freedom, the flux tube, the incredible strength at nuclear distances, the bizarre weakening at short distances, the wildly complex dynamics inside every proton and neutron, where a sea of virtual gluons constantly appears and disappears, branching and merging and interacting with itself in an endless quantum storm. All of it traces back to a single fact. Gluons carry color charge. There are 8 types of gluons, each carrying its own specific combination of color and anticolor. Compare that to the electromagnetic force, which has exactly one type of photon carrying no charge whatsoever. The strong force is richer, more layered, more deeply tangled. Its mathematical structure belongs to a class of theories called non-abelian gauge theories. The word non-abelian, named after the mathematician Niels Henrik Abel, is the technical way of saying the force carriers interact with each other. Abelian theories, like electromagnetism, have neutral force carriers. Non-abelian theories, like quantum chromodynamics, have force carriers that carry the charge of their own force and therefore interact among themselves. The weak force is also non-abelian. Its carriers, the W and Z bosons, carry weak charge and do interact with one another. But the weak force operates very differently from the strong force. Its carriers are extremely heavy, over 80 times the mass of a proton, which makes the weak force short-ranged and relatively feeble at everyday distances. The self-interactions of W and Z bosons don't produce confinement. They don't create flux tubes. The strong force, with its massless gluons and its particular 3-color mathematical structure, is unique in producing the kind of intense, distance-independent binding that makes confinement inescapable and that makes glueballs theoretically possible. So let's take stock of where we are. The strong force is carried by gluons. Gluons carry color charge. Because they carry color charge, gluons feel the strong force themselves. They interact with each other. They pull on each other. They can emit and absorb other gluons. This self-interaction is responsible for confinement, the absolute law that color-charged particles can never be isolated. It's responsible for asymptotic freedom, the strange weakening of the force at very short distances. And it opens the door to a possibility that exists nowhere else in the known laws of physics. If gluons interact with each other so powerfully, if they pull on each other with the same overwhelming force that binds quarks into protons and neutrons, then what stops gluons from binding to each other directly? What stops a collection of gluons from forming a self-contained knot, a particle with no quarks inside it at all, a bound state made entirely from the carriers of the strong force? The answer is, nothing stops it. The mathematics of quantum chromodynamics doesn't just allow glueballs to exist, it demands them. The same equations that predict confinement, the same equations that predict the masses of protons and neutrons with remarkable accuracy, the same equations that correctly describe asymptotic freedom and the behavior of quarks at the highest energies our particle accelerators can reach, those same equations predict that bound states of pure gluons must be part of the particle spectrum of our universe. Glueballs aren't a loophole that clever theorists found in the margins. They aren't speculation. They aren't wishful thinking. They're a direct, unavoidable mathematical consequence of the theory that successfully describes everything else about the strong force. The universe, according to our best and most thoroughly tested understanding of the strong force, must contain particles that are built from force carriers alone. No quarks, no antiquarks, no ordinary matter of any kind. Just gluons interacting with each other, bound together by the very force they themselves carry. A particle made from its own glue. And yet, after more than 4 decades of active searching, confirming the existence of a glueball in an actual experiment has proved to be one of the most frustratingly difficult challenges in all of particle physics. The mathematics says they must be out there. The experiments say that finding them is a nightmare. Understanding why, understanding the infuriating obstacles that stand between the theory's prediction and experimental proof, requires diving much deeper into the strange, tangled, profoundly quantum world where the strong force builds its particles. So gluons interact with each other. They carry the charge of their own force. They pull on one another with the same overwhelming strength that locks quarks into protons. and the mathematics says they can form bound states entirely on their own. But to fully appreciate how strange that would be, you need to see what ordinary particles look like from the inside. Because the glueball's true strangeness only becomes visible when you hold it up against the particles physicists already know. Every particle you've ever interacted with, every atom in your body, every element on the periodic table, is built from composite particles called hadrons. Hadrons are particles assembled from quarks, bound together by gluons. There are two types. The first is called a baryon. A baryon contains 3 quarks. The proton, which sits at the heart of every atom, is a baryon. 2 up quarks and 1 down quark, bound together by a furious storm of gluon activity. The neutron is also a baryon, 1 up quark and 2 down quarks, held together by the same force. Every atomic nucleus in the universe, from the single proton in hydrogen to the 92 protons and roughly 146 neutrons in uranium, is built from baryons. The second type of hadron is called a meson. A meson is simpler in its makeup. It contains just 1 quark and 1 antiquark, bound together by gluons. Mesons are less familiar than protons and neutrons because they're unstable. They don't last long enough to build atoms. They appear briefly in high-energy collisions, in cosmic ray showers, in the decay products of heavier particles, and then they fall apart within tiny fractions of a second. But during their brief existence, they're real particles with definite masses, definite lifetimes, and definite properties that physicists measure with impressive precision. So the recipe for every known hadron is straightforward. Take quarks, add gluons to bind them. Quarks provide the particle's identity. Gluons provide the binding force. 3 quarks make a baryon. A quark and an antiquark make a meson. Every hadron ever detected follows this template, no exceptions, until you consider the glueball. A glueball breaks the template completely. There are no quarks playing the role of bricks. There are no fundamental matter particles providing the skeleton of the structure. Instead, the mortar itself has formed a structure on its own. The gluons, which are supposed to be the binding force between quarks, have bound to each other instead, creating a self-contained particle with no valence quarks inside it whatsoever. Imagine building a house. Normally you use bricks for the walls and cement to hold the bricks together. Bricks provide structure. Cement provides adhesion. Now imagine removing every single brick, and somehow the cement alone has hardened into a freestanding structure, a solid object that holds its own shape. A house made entirely of cement. That's roughly what a glueball is, a particle made entirely of the substance that was supposed to be holding other particles together. And the logic demanding its existence is airtight when you think it through. Remember that confinement, the absolute rule preventing any color-charged particle from existing in isolation, is one of the strongest laws in nature. Confinement demands that every object carrying color charge must bind into a color-neutral combination. Quarks satisfy this requirement by forming hadrons. 3 quarks in a baryon carry 1 red charge, 1 green charge, and 1 blue charge, which add up to color neutral, like mixing 3 primary colors of light to make white. A quark and antiquark in a meson carry a color paired with its matching anticolor, which also cancels to neutral. Every hadron is a color-neutral package. That's the rule. But quarks aren't the only particles carrying color charge. Gluons carry it too. Each gluon carries a combination of a color and an anticolor charge, and confinement makes no exceptions. It doesn't say only quarks must form color-neutral packages. It says everything carrying color charge must form color-neutral packages. So, if gluons carry color charge, then the same law that forces quarks into color-neutral groups must also permit, and in fact require, gluons to form color-neutral combinations of their own. A group of gluons whose color charges combine to zero net color would be perfectly legitimate. It would satisfy confinement. It would be a bound state of pure gluon field. It would be a glueball. This isn't a loophole that clever theorists found in the margins. It's a direct, logical consequence of two properties that are both thoroughly established. Gluons carry color charge, and confinement forbids any color-charged object from existing in isolation. Put those two facts together, and glueballs are inevitable. But saying the math demands glueballs is one thing. Actually calculating what a glueball should look like, how heavy it should be, what quantum properties it should carry, that requires solving the equations of quantum chromodynamics. And this is where the story takes a turn that surprises most people outside of physics. Because those equations are, for all practical purposes, unsolvable by hand. Quantum chromodynamics is almost uniquely difficult among physical theories. In electromagnetism, you can often solve problems with pen and paper. The math is demanding, but it's manageable.
You write down the equations, apply some well-tested techniques, and after enough algebra, you get an answer. Physicists have been doing this successfully for more than a century. The reason this works is that the electromagnetic force is relatively weak. The coupling constant, the number that measures how strongly particles interact, is small, about 1 divided by 137. Because this number is small, you can use a mathematical technique called perturbation theory. You start with a simple approximate solution and then add small corrections, layer by layer, each correction smaller than the last. The series converges. Each step brings you closer to the true answer. It's like calculating the value of pi by adding smaller and smaller corrections to an initial estimate. Your first guess is rough, but each refinement makes it better. The strong force doesn't allow this luxury. At the distances that matter for hadron physics, deep inside protons and neutrons and glueballs, the strong coupling constant is not small, it's close to 1. This means perturbation theory's corrections aren't small at all. Each correction is roughly the same size as the one before it. The series doesn't converge. It doesn't settle toward an answer. It oscillates wildly, producing nonsense. The standard mathematical machinery that works so beautifully for electromagnetism simply collapses when applied to the strong force at these energy scales. Asymptotic freedom, the remarkable weakening of the strong force at very short distances, saves perturbation theory in certain situations. When quarks are smashed together at extremely high energies in a particle collider, the effective coupling becomes small, and standard calculation methods work. This is why quantum chromodynamics makes excellent predictions for high-energy scattering experiments. But glueballs are bound states. They exist at the energy scales where the strong force is strongest, precisely the regime where perturbation theory fails. Calculating glueball properties requires a completely different approach. The answer came in 1974 from the physicist Kenneth Wilson, and it was revolutionary. Wilson proposed a method called lattice gauge theory. The idea is elegant and brutal in equal measure. Instead of trying to solve the equations of quantum chromodynamics in continuous space-time, where every point in space has a value and the number of variables is literally infinite, you replace continuous space-time with a discrete grid, a lattice. You put space-time on graph paper. You turn the smooth fabric of space and time into a finite collection of points connected by links. Quarks sit on the lattice points. Gluon fields live on the links connecting those points. The continuous equations, which are impossible to solve exactly, become a set of discrete equations on the lattice, which can be solved numerically by a computer. This is not a simplification in the way that rounding off a number is a simplification. It makes the problem computable instead of impossible. The computation remains enormously difficult. Even on a modest lattice, say 32 points in each spatial direction and 64 points in the time direction, the number of variables is staggering. Each link carries information about the gluon field at that location, encoded as a mathematical object called a matrix. The calculation involves summing over all possible configurations of these matrices across the entire lattice, weighted by their quantum mechanical probability. This is a sum over an astronomically large number of possibilities. No computer in existence can evaluate every single one. Instead,
physicists use a technique called Monte Carlo simulation, named after the famous casino, because it relies on randomness. They randomly generate configurations of the gluon field according to their quantum mechanical probability. Each random configuration is like a snapshot of the gluon field at one particular instant, capturing one possible arrangement of all the gluon field values across the lattice. Generate enough snapshots, thousands or even millions of them, measure the property you're interested in for each snapshot, average the results, and you converge toward the true quantum mechanical answer. The more snapshots you generate, the more precise your result becomes. It's statistics applied to quantum field theory. This is what lattice quantum chromodynamics looks like in practice. Enormous supercomputers running for months, billions of random numbers generated, millions of gluon field configurations sampled, properties measured and averaged. It's not elegant in the way that solving an equation with pen and paper is elegant, but it works, and for certain quantities, it gives answers that are astonishingly precise. The first serious numerical lattice calculations were performed around 1980, and the field has advanced enormously since then as computers have grown more powerful and algorithms have grown more sophisticated. Modern lattice calculations can predict the mass of the proton to within roughly 1% of its experimentally measured value. They correctly reproduce the masses of dozens of known hadrons, particles whose properties have been measured in accelerator experiments with great precision. These aren't rough guesses or order of magnitude estimates. They're quantitative predictions that match real-world measurements. When a computational method correctly predicts the masses of dozens of known particles, you develop considerable confidence in its predictions for particles that haven't been confirmed yet. And this is exactly what lattice calculations have done for glueballs. Multiple independent research groups around the world, using different lattice sizes, different computational techniques, different software, and different supercomputers, have all calculated the predicted masses and properties of glueball states. The fact that these independent calculations agree with each other is a powerful sign that the predictions are robust. They aren't artifacts of one particular method or one particular approximation. They emerge consistently from the theory itself. But there's a subtlety here that matters enormously, and understanding it requires knowing a bit more about how lattice physicists actually extract glueball masses from their calculations. Here's the essential idea. In quantum field theory, you can learn about particles by studying how disturbances in a field propagate across space and time. If you create a disturbance at one point and measure whether a similar disturbance appears at another point some distance away, the strength of that correlation tells you something about the particles that carry information through that field. In particular, the rate at which the correlation fades as you increase the distance reveals the mass of the lightest particle that can be exchanged between the 2 points. Heavy particles produce correlations that die off quickly. Light particles produce correlations that persist over longer distances. Massless particles produce correlations that extend indefinitely. On the lattice, physicists exploit this principle directly. They construct mathematical operators designed to create disturbances in the gluon field with specific quantum properties. They want an operator that produces exactly the kind of gluon field configuration a glueball would represent. A localized knot of gluon energy with zero spin, positive parity, and positive charge conjugation, matching the predicted lightest glueball's quantum numbers. They place this operator at one point on the lattice and a matching operator at another point some distance away in the time direction. Then they measure how the correlation between these two operators decays as the separation increases. If a glueball state exists with the quantum numbers matching those operators, the correlation function will decay at a rate determined by the glueball's mass. A heavier glueball produces a faster decay. A lighter glueball produces a slower decay. By fitting the measured correlation to a mathematical curve, physicists extract the glueball mass from the data.
This is how all hadron masses are calculated on the lattice, not just glueball masses. Protons, neutrons, mesons, all of them are extracted from correlation functions using the same basic procedure. For glueballs, though, the calculation is technically harder than for ordinary hadrons. The signal is noisier. Glueball correlation functions tend to decay very quickly, which means the useful signal is concentrated in a narrow range of lattice separations. Extracting a clean mass value requires large lattices, high statistics, and careful control of systematic errors. Physicists have developed specialized techniques to improve the signal, including methods called smearing and variational analysis, where they construct multiple different glueball operators and combine them to find the combination that overlaps most strongly with the true glueball state. These techniques have matured considerably over decades, and modern calculations achieve impressive precision. Here's another crucial distinction. The earliest and cleanest lattice glueball calculations were performed in what physicists call the quenched approximation. In a quenched calculation, you include only gluons on the lattice. You leave out the quarks entirely. This simplifies the computation enormously, because quarks are technically very expensive to include. Their mathematical properties require inverting enormous matrices at every step of the Monte Carlo simulation, which dramatically increases the computational cost. By leaving quarks out, you can use larger lattices, generate more configurations, and achieve better statistical precision. In the quenched approximation, glueball calculations are remarkably clean. Because there are no quarks in the simulation, there are no quark-antiquark mesons for the glueball to mix with. The glueball states are pure. Their masses are well defined. The lightest scalar glueball comes out at roughly 1600 to 1700 mega-electron volts, with a precision of a few percent. The tensor glueball, the one with spin 2, comes out at roughly 2300 to 2400 mega-electron volts. These numbers have been confirmed by multiple independent groups and are considered reliable predictions of the pure glue sector of quantum chromodynamics. But the real universe is not quenched. The real universe contains quarks. Virtual quark-antiquark pairs constantly bubble in and out of existence inside the quantum vacuum, and these virtual quarks interact with the gluon field. In a full, unquenched calculation, you include dynamical quarks on the lattice. This makes the calculation much harder, but it also makes it more realistic. And it introduces precisely the complication that makes glueball identification so difficult in experiments: mixing. When quarks are included in the lattice simulation, the pure glueball state can mix with quark-antiquark meson states that have the same quantum numbers. The neat, clean glueball of the quenched approximation gets smeared out. Its identity blends with nearby mesons. The physical particles you extract from the unquenched lattice are no longer pure glueball or pure meson. They're mixtures, exactly as they would be in nature. Unquenched glueball calculations are at the frontier of current lattice research. They are computationally demanding to the point of being heroic. The mixing between glueball and meson states introduces additional technical challenges, requiring sophisticated methods to disentangle the different contributions. Progress has been steady, but slower than in the quenched sector. Several groups have published preliminary unquenched glueball results, and the picture that emerges is broadly consistent with expectations. The glueball doesn't disappear when quarks are included. Its mass shifts somewhat, and its identity smears across multiple physical states through mixing, but the underlying glueball component remains present. It doesn't dissolve. It persists as a real contribution to the particle spectrum, even in the full theory with quarks. This matters because some skeptics have wondered whether glueballs might be an artifact of the quenched approximation, existing only in a simplified world without quarks. The unquenched calculations, while still being refined, strongly suggest otherwise. Glueballs survive the inclusion of quarks. Their properties change through mixing, but they remain real features of the theory, not computational ghosts. The lightest glueball, the one most accessible to experiments, is predicted to be a scalar particle. Scalar means it has no spin, it doesn't rotate, it has no preferred axis. It's the simplest possible type of particle, a featureless lump of bound gluon field. Its predicted mass is roughly 1600 to 1700 megaelectronvolts. Megaelectronvolts are the units physicists use for subatomic particle masses because Einstein showed that mass and energy are interchangeable, and measuring mass in energy units is natural at this scale. To put that number in context, the proton has a mass of about 938 megaelectronvolts, so the lightest predicted glueball is roughly 1.7 to 1.8 times heavier than a proton. It's in a mass range where existing experiments can produce and detect particles. It's heavy enough to be interesting, but not so heavy that you'd need a completely new generation of accelerators to create it. The next glueball state predicted by lattice calculations is a tensor particle, meaning it carries spin 2. This one is heavier, with a predicted mass of roughly 2300 to 2400 megaelectronvolts, about 2.5 times the proton mass. Beyond that, there are additional predicted states at even higher masses, including a pseudoscalar glueball at around 2600 megaelectronvolts, and still heavier states beyond. The full predicted spectrum forms a ladder of glueball states with increasing masses, each carrying specific quantum properties that distinguish it from the others. These are not vague forecasts. They come from rigorous, reproducible calculations, cross-checked by independent groups using independent methods. The lightest scalar glueball mass, in particular, is one of the best established predictions of lattice quantum chromodynamics. If the theory is correct, and it has been correct about virtually everything else it has been tested against, then particles matching these descriptions must exist somewhere in nature. Now let's address the simplification in the title, because when we say a glueball is made of pure force, that's a dramatic and attention-grabbing way to put it, but it needs a careful qualifier. A glueball is not made of nothing. It's not some magical entity with no physical substance. It's not a particle conjured from thin air. A glueball is made of gluons, and gluons are real physical objects. They are excitations of the gluon field, one of the fundamental quantum fields permeating all of space. They carry energy, they carry momentum, they exert forces. They are, by every physical measure, real things. And energy, as Einstein showed, has mass. This is the deep lesson of the famous equivalence between energy and mass. When gluons bind together inside a glueball, the energy of their interactions, the kinetic energy of their motion, the potential energy stored in the gluon field that binds them, all of that energy contributes to the glueball's mass. The glueball weighs something not because it contains heavy ingredients, but because the energy of the binding process itself has weight. The force, through its energy, creates the mass. This might sound exotic, but it's actually the exact same mechanism that gives you most of your own mass. And this is a fact that surprises nearly everyone who hears it for the first time. The proton has a mass of about 938 megaelectronvolts, but the quarks inside it, 2 up quarks and 1 down quark, have masses of only about 2 to 5 megaelectronvolts each. Add up all 3 quark masses and you get roughly 10 megaelectronvolts. That's barely 1% of the proton's total mass. Over 99% of the proton's mass comes from somewhere else entirely. It comes from the energy of the gluon field binding the quarks together. It comes from the kinetic energy of the quarks racing around inside the proton at tremendous speeds. It comes from the constant storm of virtual gluons being emitted and absorbed, splitting and merging, creating and destroying virtual quark-antiquark pairs in an endless turbulent cycle. All of that activity carries energy, and all of that energy has mass. You are made of atoms. Atoms are made of protons and neutrons, and protons and neutrons get over 99% of their mass not from the quarks inside them, but from the energy of the gluon field. You already are, in a very real and measurable sense, made mostly of gluon energy. The mass you feel when you step on a scale, the weight that holds you to the earth, is overwhelmingly the energy of the strong force, expressed as mass through Einstein's equation. The quarks contribute almost nothing to that number. The gluon field contributes nearly everything. So when we say a glueball is made of pure force, what we really mean is that it takes this mechanism to its logical extreme. In a proton, quark masses contribute roughly 1% of the total, and gluon field energy contributes the other 99%. In a glueball, quark masses contribute exactly 0%. The entire mass comes from the energy of the gluon field interacting with itself. There are no valence quarks providing even a token contribution. It's all gluons, all force energy, all the way down. This doesn't make the glueball made of nothing. It makes the glueball made of the same stuff that already provides most of the mass of every atom in the universe. The gluon field isn't some ethereal abstraction. It's the dominant source of mass in all visible matter. Every star, every planet, every grain of sand, every cell in your body owes the overwhelming majority of its mass to the energy of the gluon field inside its protons and neutrons. A glueball is simply a particle where this mechanism operates in its purest form, without even the modest 1% contribution of quark rest masses. This perspective transforms how you should think about the boundary between force and matter. At the deepest level, that boundary is blurry. What we call matter, the solid stuff of the world, the things you can touch and hold and weigh, is overwhelmingly composed of force energy that has been given mass through the equivalence of energy and mass. Quarks are real, but they're featherweight. The gluon field is what makes things heavy. The glueball simply reveals this truth in its starkest form. And when physicists probe the interior of a proton using high-energy collisions, firing fast-moving particles deep inside to see what's there, they find direct confirmation of this picture. Gluons carry roughly half of the proton's total momentum. Half. The gluons aren't passive background players, quietly holding quarks in place. They're carrying as much momentum as all the quarks combined. The proton is, by measurement, about as much gluon as it is quark. Its interior is dominated by gluon field dynamics. Gluons emitting gluons. Gluons splitting into quark-antiquark pairs. Gluons merging together. Gluons interacting with themselves in an extraordinarily complex web of quantum processes that generates most of the mass you experience in daily life. Given all of this, the existence of a pure gluon-bound state stops seeming exotic. If the gluon field already dominates the interior of every proton, if gluons already carry half the momentum and generate over 99% of the mass, then asking whether gluons can form a bound state on their own is almost like asking whether ocean water can form a wave without a boat. The ingredients are already there. The interactions are already there. The binding mechanism is already there. All you need is for the gluon field to find a configuration where it binds to itself without any quarks present. And the mathematics says such configurations don't just exist as rare possibilities requiring extraordinary conditions. They're a natural, expected part of the particle spectrum. Glueballs should be produced in any sufficiently energetic collision involving the strong force. They should be there, lurking among the other particles, created routinely in the firestorms of collider experiments. The real challenge has never been whether glueballs exist in the theory. The theory is emphatic. They must.
The real challenge is something far more frustrating. It's the question of how you actually identify a glue ball once it's been created. Because glue balls, as we're about to discover, don't carry a label. They don't announce themselves. They look, from the outside, almost exactly like certain ordinary mesons. And distinguishing a glue ball from a meson that merely resembles one turns out to be one of the most maddening problems in all of experimental physics. You might think that finding a glue ball would be straightforward. The theory predicts specific masses. Physicists have enormous particle accelerators capable of producing particles in exactly the right mass range. Modern detectors can track individual subatomic particles with exquisite precision, measuring their energies, their trajectories, and their identities with remarkable accuracy. You know roughly what you're looking for, and you know roughly where to look. How hard can it be? The answer is that it's among the hardest identification problems in all of particle physics. Not because glue balls are too heavy to produce, not because the accelerators aren't powerful enough, not because the detectors lack sensitivity. The problem is far more fundamental than any of those things. The problem is that a glue ball, once it's produced, looks almost exactly like several ordinary particles that are made of quarks. There is no unique stamp, no exclusive signature, no unmistakable fingerprint that screams, "This is a glue ball and not something else." A glue ball decays into the same products as certain quark-antiquark mesons. It carries the same quantum labels. From the outside, it is nearly indistinguishable from ordinary matter. And that single fact has turned the search for glue balls into one of the most painstaking detective stories in the history of science. To understand why this is so frustrating, you need to understand how physicists classify particles. Because in the subatomic world, particles don't have colors or shapes or textures that you can use to tell them apart. They have quantum numbers. And quantum numbers are everything. Every particle in nature carries a set of quantum properties that define what it is and how it behaves. These properties include spin, which describes how the particle rotates; parity, which describes how the particle behaves when you flip it in a mirror, reversing left and right; and charge conjugation, which describes how the particle behaves when you swap every particle for its antiparticle. Together, these three properties form a kind of identity code. Physicists write them as a compact label, a set of numbers and signs that uniquely categorize the particle's quantum behavior.
Here's the trouble. The lightest predicted glue ball, the scalar one with a mass around 1600 to 1700 megaelectron volts, carries the simplest possible set of quantum numbers: zero spin, positive parity, positive charge conjugation. It's the most featureless, most generic quantum identity a particle can have. And there are several ordinary quark-antiquark mesons in exactly the same mass range that carry exactly the same quantum numbers. They are, by their quantum identity code, the same type of object. The glue ball's identity card matches theirs perfectly. This means a glue ball decays into the same types of particles that these ordinary mesons decay into. It produces the same sprays of pions and kaons and eta particles in the detector. When it appears in an experiment, it doesn't arrive with a banner announcing its origin. It just shows up as a bump in the data, a statistical excess of events at a particular mass, indistinguishable at first glance from an ordinary meson resonance. You can't point at a single event in the detector and say with confidence that this particular particle was a glue ball rather than a quark-antiquark meson. The individual decays look the same. Only by studying patterns across millions of events, looking for subtle statistical differences in production rates and decay preferences, can you begin to tease apart whether something unusual is happening? And as if that weren't difficult enough, there is a second problem that makes the situation dramatically worse. Quantum mechanics allows particles with the same quantum numbers to mix. This is one of the most counterintuitive features of quantum mechanics, and it's absolutely central to the glueball search. In the everyday world, objects have definite identities. A cat is a cat. A dog is a dog. A cat doesn't spontaneously become half cat and half dog. But in quantum mechanics, if two states have the same quantum numbers, they can superpose. They can blend. The physical particles that actually exist in nature aren't necessarily pure states. They can be mixtures. And this mixing fundamentally changes what you observe. Imagine you have a pure glueball state and a pure quark-antiquark meson state, both with the same quantum numbers and similar masses. In the mathematics of quantum mechanics, these two states don't stay separate. They mix. They blend into each other like two colours of paint stirred together. The physical particles that emerge from this mixing are neither pure glueball nor pure meson. They're superpositions. Each physical particle contains some fraction of glueball character and some fraction of meson character. This means there may not be a single particle sitting in the detector that is purely a glueball. Instead, the glueball's identity is smeared across multiple physical particles. One meson might be 80% quark-antiquark and 20% glueball. Another nearby meson might be 60% quark-antiquark and 40% glueball. A third might be 30% quark-antiquark and 70% glueball. The glueball character is distributed. It's shared. It leaks into the ordinary meson spectrum, contaminating it, and the ordinary meson character leaks back into the glueball state. This is not a theoretical curiosity. Mixing is expected to be significant precisely in the mass range where the lightest glueball is predicted to appear. Lattice calculations predict the lightest glueball at around 1600 to 1700 megaelectron volts. And there are well-established quark-antiquark mesons at nearly the same masses with the same quantum numbers. These are exactly the conditions under which quantum mechanical mixing should be strong. The glueball and the mesons are close neighbours with identical quantum identities, and quantum mechanics insists that such neighbours blend. The consequence for experimentalists is devastating. You can't just look for one particle with the right mass and the right quantum numbers and declare victory. Even if you find exactly the particle that lattice calculations predict, it might not be a pure glueball. It might be a meson with significant glueball admixture, or it might be a glueball with significant meson admixture. Determining the glueball content of a physical particle requires not just measuring its mass and quantum numbers, but measuring its production rates and decay patterns with enormous precision, and comparing them to detailed theoretical models of mixing. It's forensic accounting at the subatomic level. So if the glueball can't be identified by its quantum numbers, and it can't be identified by its decay products, and it mixes with ordinary mesons so thoroughly that no single particle may be a pure glueball, then how on earth do physicists approach this problem? The answer involves two interlocking strategies. One focuses on where and how a particle is produced. The other focuses on the detailed pattern of how it decays. Neither strategy works in isolation, but together they create a web of evidence that can distinguish glueball-like behaviour from ordinary meson behaviour, even when no single measurement is decisive on its own. Let's start with production. The core logic is simple and powerful. A glueball is made of gluons. Therefore, it should be produced most abundantly in physical processes that are dominated by gluon activity. Conversely, it should be produced weakly or not at all, in processes where gluons play a minimal role. If you find a particle that appears strongly in gluon-rich environments, but is conspicuously absent or suppressed in gluon-poor environments, that asymmetry is a powerful clue. It suggests the particle has significant gluon content. An ordinary quark-antiquark meson wouldn't show that pattern because its production depends on having the right quark flavors available, not on having an abundance of gluons. This leads to a specific prediction that experimentalists call the stickiness test, though not always by that name. Consider two different ways to produce particles. In the first, you use a process dominated by gluon activity, like the radiative decay of a J-psi particle. In the second, you use a process dominated by photon activity, like the collision of two photons. These two processes probe different aspects of a particle's inner structure. The gluon-rich process probes how strongly a particle couples to gluons. The photon-rich process probes how strongly a particle couples to electrically charged quarks, because photons interact with electric charge, not with color charge. A glueball, being made entirely of gluons, should couple strongly to gluons but weakly to photons. Gluons don't carry electric charge. Photons don't carry color charge. The two don't interact directly. A pure glueball has no quarks inside it, and therefore no electric charge for a photon to grab onto. So a glueball should be produced copiously in gluon-dominated processes and should be strongly suppressed in photon-dominated processes. An ordinary quark-antiquark meson shows the opposite pattern. It contains quarks, which carry electric charge, so it couples naturally to photons. It also couples to gluons because quarks carry color charge. But the ratio of its photon production to its gluon production follows a specific pattern determined by the charges of the quarks inside it. A glueball's ratio would be dramatically different. Very high gluon production, very low photon production. This production asymmetry is one of the strongest diagnostic tools available. If a particle appears powerfully in radiative J-psi decays, where the production mechanism is overwhelmingly gluonic, but is barely visible or absent in two-photon collisions, where the production mechanism is purely electromagnetic, that's a smoking gun for significant gluon content.
It doesn't prove the particle is a glueball on its own, because mixing complicates things. A particle that is 70% glueball and 30% quark-antiquark meson would show up in both gluon-rich and photon-rich processes, just with different relative strengths. But the pattern of strengths constrains the mixing fractions. It tells you how much glueball character the particle carries. Now let's turn to the second strategy, decay patterns. This is where the concept of flavor blindness becomes essential. A glueball contains no quarks. It has no preferred quark flavor. It doesn't know the difference between an up quark and a strange quark. Gluons interact with all quark flavors with exactly the same strength, because the strong force doesn't care about flavor. It only cares about color charge, and all quarks carry the same types of color charge, regardless of whether they're up, down, or strange. So, when a glueball decays, when it converts its gluon energy into quark-antiquark pairs that then form the pions and kaons and eta particles you actually detect, it should produce all quark flavors with roughly equal probability. The only thing breaking perfect equality is the mass differences between quark flavors. Strange quarks are heavier than up and down quarks, so producing a pair of strange quarks requires slightly more energy than producing a pair of up or down quarks. But aside from this kinematic correction, the coupling itself is flavor blind. This is fundamentally different from how ordinary quark-antiquark mesons decay. An ordinary meson contains specific quark flavors, and those flavors strongly influence which decay channels dominate. A meson made primarily of up and down quarks will preferentially decay into pions, which are themselves made of up and down quarks. A meson with a large strange quark component will preferentially decay into kaons, which contain strange quarks.
The decay pattern reflects the quark content. It's like a fingerprint revealing the particle's internal composition. A glueball's decay fingerprint would look different. It would not strongly favor any particular channel over another. Its branching ratios, the percentages of decays going into different final states, would follow a pattern dictated by flavor symmetry and phase space, rather than by internal quark content. If you measure a particle's decay into pion pairs, kaon pairs, and eta pairs, and the ratios match the flavor-blind prediction, rather than the pattern expected for any specific quark-antiquark combination, that's evidence for glueball content. Combining these two strategies, production asymmetry and flavor-blind decays, gives experimentalists a multidimensional diagnostic. No single measurement is conclusive, but a particle that shows enhanced production in gluon-rich processes, suppressed production in photon-rich processes, and flavor-blind decay ratios presents a consistent picture that's very difficult to explain without invoking significant glueball content. Each piece of evidence constrains the interpretation. Together, they build a circumstantial case that can become compelling even in the absence of a single decisive measurement. This is the toolkit physicists bring to the glueball search. Now let's look at the specific gluon-rich processes where these tools are applied. The single most important gluon-rich process for the glueball search involves a particle called the BESIII. The BESIII is a meson made of a charm quark and a charm antiquark, bound together by the strong force. It was discovered in 1974, and its discovery was so significant that it triggered what physicists call the November Revolution, a rapid transformation in how the physics community understood quarks and the strong force. The BESIII is heavy, with a mass of about 3,097 mega-electron volts, more than 3 times the mass of a proton, and it has a special property that makes it extraordinarily useful for glueball searches. When the BESIII decays, one of its most important decay modes involves emitting a photon, a particle of light, plus other particles. This is called a radiative decay. The photon carries away some of the energy, and the remaining energy is converted into other particles through the strong force. Here's the crucial point. In this process, the charm quark and the charm antiquark annihilate each other. They vanish, converting their mass energy into a burst of gluon field activity. The result is a state that is overwhelmingly gluonic. It's a fireball of pure gluon energy, which then condenses into whatever particles the strong force permits. This is exactly the kind of environment where you'd expect glueballs to form. The photon flies off cleanly and can be detected, tagging the event and confirming that a radiative decay occurred. Whatever appears alongside the photon emerged from that gluon-rich fireball. If glueballs are produced abundantly in gluon-rich environments, then the radiative decays of the BESIII are among the best places to look. This is why a particular experiment in Beijing has become the epicenter of the glueball search. The experiment is called BESIII, and it operates at the Beijing Electron-Positron Collider, known as BEPC-2. This facility collides electrons with their antiparticles, positrons, at precisely tuned energies. By setting the collision energy to exactly the mass of the BESIII, about 3,097 megaelectron volts, the collider produces BESIII particles in enormous quantities, billions of them. Each one is a potential source of glueball production through radiative decay. No other facility on Earth produces BESIII particles at this rate with this level of control. BESIII collected roughly 10 billion BESIII events by the early 2020s. 10 billion. Each event produces a spray of particles that must be individually tracked, identified, and measured. The scale of data is staggering, and processing it requires years of painstaking computational analysis. But the sheer volume is essential, because the signal you're looking for is subtle. You're not looking for an obvious new particle appearing clearly above the background. You're looking for slight excesses, small statistical bumps, tiny deviations from what you'd expect if only ordinary quark-antiquark mesons were being produced.
Another production mechanism that physicists exploit is called central exclusive production. This occurs in proton-proton collisions, where two protons approach each other at high energy but interact in a very specific way. Instead of smashing into each other head-on and producing a chaotic explosion of debris, the protons exchange gluon bundles and emerge intact on the other side. They graze past each other, and in the space between them, the exchanged gluon fields materialize into particles. The protons survive. The new particles appear in the gap between them. This process is gluon-dominated. The exchanged objects, called pomerons, are thought to be built primarily from gluon field configurations. So any particles produced in the central region emerged from a gluon-rich environment, making them promising candidates for glueball searches. Experiments at CERN, particularly the WA102 experiment in the 1990s, and more recent studies at the LHCb detector, have used central exclusive production to search for glueball signals. The technique is powerful because the surviving protons provide additional constraints on what happened in the collision. By measuring the protons' final energies and angles, you can reconstruct the properties of whatever was produced between them with impressive precision. But whether you're using J-psi radiative decays or central exclusive production, or any other technique, the fundamental experimental challenge remains the same. You're looking for subtle signals buried in enormous backgrounds, and extracting those signals requires an analytical technique called partial wave analysis, which is one of the most mathematically demanding procedures in experimental physics. Here's what partial wave analysis involves. When particles are produced in a collision and then decay into lighter particles, the angular distribution of those decay products, the directions in which they fly, carries information about the spin and quantum numbers of the parent particle. A particle with 0 spin decays differently from a particle with spin 1, which decays differently from a particle with spin 2. By carefully measuring the angles between all the decay products across thousands or millions of events, you can work backward to determine what particles were produced and what their quantum properties were. But you don't have just one particle being produced. You have many different particle states all being produced simultaneously, overlapping in mass, interfering with each other quantum mechanically, each decaying into the same final products. The data you actually see in the detector is a tangled superposition of all these contributions. Partial wave analysis is the process of mathematically untangling this superposition. You build a model that includes every known particle state that could contribute, plus any new states you're trying to test for. You assign each state its quantum numbers, its mass, its width, and its coupling strengths to the decay products. Then you fit this model to the data, adjusting all the parameters simultaneously until the model matches what the detector actually observed. This involves fitting dozens of parameters at once across millions of data points. The mathematical space of possible solutions is vast. There are local minima, ambiguities, and technical subtleties at every step. Different assumptions about which states to include in the model can lead to different conclusions about what the data are telling you. Two equally competent research groups analyzing the same dataset can arrive at different answers if they make different modeling choices. This is not because one group is wrong and the other is right. It's because the data are genuinely ambiguous in certain regions. The signal you're looking for is fragile. It can appear or disappear depending on how you handle the background. And this is precisely why studying multiple decay channels simultaneously is so important. If you only look at decays into pion pairs, you see one slice of the data, contaminated by its own set of backgrounds and its own systematic uncertainties. If you only look at decays into kaon pairs, you see a different slice with different complications. But if you analyze both channels at the same time, requiring that the same set of particle states, with the same masses and the same quantum numbers, explains both datasets simultaneously, you dramatically reduce the ambiguity.
A background fluctuation that mimics a glueball signal in the pion channel is unlikely to also mimic it in the kaon channel in a way that's consistent with flavor-blind decay. The more channels you include, the more constrained the fit becomes, and the harder it is for a spurious signal to survive. This multi-channel approach is one of the most important methodological advances in recent glueball searches. Earlier analyses tended to study individual decay channels in isolation, leading to conflicting claims and persistent ambiguity. Modern analyses at BESIII and elsewhere increasingly fit multiple channels simultaneously, using the correlations between channels to pin down the properties of each contributing state. It's more computationally demanding, more mathematically complex, and requires larger datasets, but it produces much more robust results. Let me walk you through how this looks in practice at BESIII, because the human effort behind these measurements is something most people never hear about. The detector itself is a marvel of engineering. It's a cylindrical machine roughly 6 meters across, built in layers like an onion. At the center, where the electrons and positrons collide, a thin beam pipe carries the circulating particles. Surrounding the collision point are concentric layers of detection systems, each designed to capture different information. A tracking system of wire chambers and silicon detectors records the trajectories of charged particles with precision measured in fractions of a millimeter. An electromagnetic calorimeter, made of dense crystals, absorbs photons and measures their energy, essential for tagging the radiative BESIII decays at the heart of the glueball search. A particle identification system distinguishes pions from kaons from protons by the different patterns they leave as they pass through matter. And the outermost layers detect muons, heavier cousins of the electron that pass through all inner layers without stopping. All of these systems generate data simultaneously. A single collision produces dozens of particles, each leaving signals in multiple detector layers. The raw data from one event is a collection of electronic signals from thousands of detector channels, and BESIII records thousands of collisions per second. The total data volume is immense, measured in petabytes. Billions of events, each containing dozens of particles, each particle leaving hundreds of electronic signals. The first task is simply to organize this flood of information. Reconstruction software takes the raw electronic signals and converts them into physics objects. It connects the dots in the tracking system to find particle trajectories. It clusters energy deposits in the calorimeter to find photon candidates. It matches tracks with particle identification signals to determine what each charged particle is. This reconstruction process is computationally intensive and must be validated extensively to ensure it's working correctly. Even small errors in reconstruction can create artificial signals that mimic what you're looking for, or can wash out genuine signals so they become invisible. Once reconstruction is complete, the analysis begins. Physicists select events that match the topology they're interested in. For a BESIII radiative decay, they might select events with exactly one high-energy photon, plus a specific combination of other particles, say 2 pions and 2 kaons. They apply quality cuts, rejecting events where the tracks are poorly measured or the particle identification is ambiguous. They apply kinematic constraints, requiring that the total energy and momentum of all detected particles match what the collider provided. These cuts reduce the data from billions of events to perhaps hundreds of thousands or a few million clean, well-measured events in the specific decay channel they're studying. Then comes the partial wave analysis. The selected events are fitted with a model containing all the known meson resonances that could contribute, plus any hypothetical new states being tested. The fit adjusts the masses, widths, and coupling constants of each state. It accounts for quantum mechanical interference between states.
It handles detector efficiency, the fact that no detector measures every particle with equal probability. Particles emitted at certain angles might escape through gaps in the detector. Particles with certain momenta might be too slow to reach the outer layers. The analysis must correct for all of these effects. The fit runs on computing clusters for hours or days. When it converges, the physicists examine the results. They check whether the data require a new state beyond the known mesons. They test what happens if they add an extra resonance in the mass region where glueballs are predicted. Does the fit improve significantly? Is the improvement statistically compelling? Or could it be explained by fluctuations in the data, by imperfect modeling of known states, or by systematic uncertainties in the detector calibration? This is where the difficulty becomes almost philosophical. Statistical significance in particle physics is measured in units called sigma, which quantify how unlikely a result would be if the signal were just a random fluctuation. A 3 sigma result means there's roughly a 1 in 750 chance the signal is a statistical fluke. A 5 sigma result means the chance of a fluke is about 1 in 3.5 million. Particle physics traditionally requires 5 sigma to claim a discovery. But 5 sigma is only meaningful if your systematic uncertainties are under control. If your model of the background is slightly wrong, if your detector calibration has a small unaccounted error, a 5 sigma statistical excess can evaporate. This is why particle physics results take years to confirm. Multiple experiments must see the same signal independently. Different analysis methods must reach the same conclusion. The systematic uncertainties must be studied exhaustively, and every possible alternative explanation must be ruled out. For glueball searches, the systematic challenges are particularly severe. The mass region where glueballs are predicted is crowded with known meson resonances. These resonances are broad, meaning their masses aren't sharply defined, but spread over a range of energies. They overlap with each other, creating a complicated interference pattern in the data. Adding a new glueball state to the model changes how all the other states fit because of quantum mechanical interference. The glueball signal doesn't sit cleanly on top of a smooth background. It's entangled with every other resonance in the region. Pulling it out requires getting every other resonance right simultaneously. Furthermore, different production mechanisms create different backgrounds and different systematic challenges. A glueball signal in J-psi radiative decays at BESIII would need to be consistent with what's seen in central exclusive production at CERN. It would need to be consistent with what's seen in other collision types at other experiments. Any credible glueball claim must survive scrutiny across multiple independent datasets, multiple production mechanisms, and multiple analysis methods. No single experiment, no matter how large or how carefully analyzed, can settle the question on its own. This is why the glueball search has stretched across decades, not because physicists are slow or careless, but because the problem is genuinely, fundamentally hard. The signal is subtle, the backgrounds are complex, the mixing is pervasive, the systematics are treacherous, and the stakes are high. Claiming the discovery of a particle made entirely from force carriers, a bound state with no quarks inside it, would be one of the most significant achievements in hadron physics. It would validate a central prediction of quantum chromodynamics in its most exotic regime. It's not the kind of claim anyone wants to get wrong. Every collaboration that publishes results on glueball candidates understands this. They spend years refining their analyses. They test their fitting procedures against simulated data where the answer is known. They vary their model assumptions systematically, checking whether their conclusions are robust or fragile. They submit their papers to peer review, where other experts in the field scrutinize every step. And even after all that, the results are typically presented with caution. Words like consistent with, suggestive of, and compatible with a glueball interpretation appear far more often than discovered or confirmed. The bar for a definitive claim is extraordinarily high, and the community has not yet unanimously agreed that it's been cleared. But the search has not been fruitless. Over the decades, several tantalizing candidates have emerged from the data. Particles that don't quite fit the expected pattern of ordinary quark-antiquark mesons. Particles whose production rates or decay patterns suggest they carry significant glueball content. Particles that show up too strongly in gluon-rich processes and too weakly in processes that should favour ordinary mesons. These candidates have been debated, challenged, defended, and reanalyzed for years. The data have grown steadily more precise, the analyses have grown steadily more sophisticated, and the picture that emerges, while still not fully settled, is increasingly pointing towards something real lurking in the data, something that can't be explained by quarks and antiquarks alone. The search for glueballs has produced a cast of suspects spanning more than 4 decades. Names appear in the literature, get debated furiously at conferences, retreat under new data, then resurface when a different experiment finds something unexpected. The story is messy, contentious, and human. It doesn't follow a clean narrative arc from mystery to revelation. Instead, it's a slow accumulation of evidence, punctuated by moments of excitement and long stretches of doubt. But through all of it, 2 candidates have remained at the centre of the conversation longer than any others. They are called F0-1500 and F0-1710. Before we discuss them, you need to understand the landscape they inhabit. In the mass range between about 1000 and 2000 mega-electron volts, where the lightest glueball is predicted to appear, there are several well-established scalar mesons, particles with zero spin, positive parity, and positive charge conjugation, the same quantum identity as the predicted glueball. The most important of these are F0980, F01370, F01500, and F01710. These 4 particles all share the same quantum numbers. They are all scalars, and they all potentially mix with a glueball state if one exists in this mass range. In a world without glueballs, the quark model provides a clear accounting of how many scalar mesons should exist. Quarks come in different flavours, up, down, and strange being the lightest 3. A quark-antiquark pair can combine in various ways, and the combinations predict a specific number of scalar meson states. The lightest scalar non-et, as physicists call it, should contain 9 states, one for each combination of quark and antiquark flavours, arranged into an octet and a singlet by the mathematics of flavour symmetry. Here's the problem. When you count the scalar mesons actually observed in experiments, there are too many. There are more scalar particles in this mass region than the quark model predicts. The quark model accounts for some of them beautifully, but there's an extra state that doesn't fit into the expected pattern. An uninvited guest at the table. Something is producing an additional particle beyond what quarks and antiquarks alone can explain. This is exactly what you'd expect if a glueball exists in this mass region and mixes with the nearby quark-antiquark states. The glueball adds an extra state to the spectrum. It inflates the population of scalars by 1, creating a surplus that pure quark-antiquark models can't accommodate. The overpopulation of the scalar meson sector has been one of the strongest circumstantial arguments for glueballs since the 1980s. Now, let's look at the 2 primary suspects. The F0-1500 was first identified clearly in the 1980s and 90s. It has a mass of about 1506 mega-electron volts and a width, meaning the range of masses over which it appears, of about 112 mega-electron volts. It was observed prominently in experiments at CERN, particularly the crystal barrel experiment operating at the low-energy antiproton ring known as LEAR, where proton-antiproton annihilations produced gluon-rich environments.
It also appeared in central exclusive production experiments like WA102, where gluon-dominated processes were specifically selected. Several properties of F0-1500 make it a strong glueball candidate. First, it is produced copiously in gluon-rich processes. In proton-antiproton annihilation, the quark and antiquark from the two colliding particles can annihilate each other, converting their energy into a burst of gluon field activity. This is similar to what happens in radiative J-psi decays. You get a gluon-rich fireball, and whatever particles emerge from that fireball are likely to contain significant gluon content. The F0-1500 appears strongly in these events, more strongly than you'd expect for an ordinary quark-antiquark meson. Second, its decay pattern is suggestive. It decays into pairs of pions and also into pairs of eta particles. The ratio of these decay modes is informative because glueball decays are expected to be flavor-blind. A glueball contains no quarks, so it has no preferred quark flavor. When it decays, it should produce up quarks, down quarks, and strange quarks with roughly equal probability, weighted only by the available energy and the quark masses. This contrasts with an ordinary quark-antiquark meson, whose decays strongly favor certain channels depending on which flavors of quarks it contains. The observed decay pattern of F0-1500 is broadly consistent with the flavor-blind expectation, though the data are not clean enough to be conclusive on their own. Third, the mass of F0-1500 sits close to the lattice prediction for the lightest scalar glueball. Not an exact match, because mixing with nearby quark-antiquark states would shift the pure glueball mass, but close enough to be consistent with the theoretical expectations. The F0-1710 is the other leading candidate, and in some ways it has an even stronger case. It has a mass of about 1704 mega-electron-volts and a width of about 123 mega-electron-volts. It was observed prominently in radiative J-psi decays, the process I described earlier, where the J-psi emits a photon and the remaining energy materializes into particles from a gluon-rich fireball. Experiments at the Mark III and DM2 detectors in the 1980s first saw the F0-1710 in radiative J-psi decays, and BESIII has confirmed and refined these observations with dramatically higher statistics. The F0-1710 appears with striking strength in these decays, significantly stronger than typical quark-antiquark mesons in the same mass range. This enhanced production in a gluon-rich process is one of the hallmarks expected of a state with large glueball content. The F0-1710 also has a distinctive decay pattern. It decays prominently into pairs of kaons rather than pairs of pions. Since kaons contain strange quarks, this tells you that whatever the F0-1710 is, it couples significantly to strange quarks. At first glance, this might seem to argue against a glueball interpretation, since glueballs should be flavor-blind. But the situation is more subtle. A glueball that mixes with a nearby strange quark-antiquark meson can acquire an enhanced coupling to strange quarks through the mixing. The mixing shifts both the mass and the decay properties of the physical state. A particle that started as a pure glueball, after mixing with a state rich in strange quarks, could end up looking like it preferentially decays into strange particles, even though the underlying glueball component was flavor-blind. This is where the story gets tangled, because the debate between the two candidates is really a debate about mixing. Most theoretical analyses agree that the physical particles we observe, F0-1500 and F0-1710, are mixtures. Neither one is a pure glueball.
neither one is a pure quark-antiquark meson. Each contains some fraction of both. The question is, which one has more glueball character? And different analyses, using different theoretical frameworks and different treatments of the mixing, have reached different conclusions. Some analyses find that F0-1500 carries the dominant glueball component. Others find that F0-1710 does. Still others suggest the glueball content is distributed more evenly across multiple states, with F0-1370 also carrying a significant share. The lattice prediction for the pure glueball mass, around 1600 to 1700 megaelectron volts, sits tantalizingly between the masses of F0-1500 and F0-1710, consistent with either candidate absorbing the majority of the glueball component after mixing redistributes the states. This ambiguity has persisted for decades, and it won't be resolved by any single measurement. It requires a comprehensive global analysis, combining data from multiple experiments, multiple production mechanisms, and multiple decay channels, all fitted simultaneously with a mixing model that accounts for the glueball and all relevant quark-antiquark states. This is exactly the kind of analysis that the field has been working toward, and recent years have brought genuine progress. In 2023 and 2024, the BESIII collaboration published new results from analyses of radiative J-psi decays, using their enormous dataset of roughly 10 billion J-psi events. These analyses applied sophisticated partial wave analysis techniques to multiple decay channels simultaneously, extracting the properties of scalar states with unprecedented statistical precision. The results provided new measurements of the production rates and decay patterns of both F0-1500 and F0-1710 in the gluon-rich radiative J-psi environment. The data are suggestive. The F0-1710 in particular continues to show anomalously strong production in radiative J-psi decays, significantly exceeding what standard quark-antiquark models predict. Several independent analyses of the BESIII data have found that the pattern of scalar meson production in these decays is difficult to explain without including a state with substantial glueball content. The F0-1710's behavior in these data is more consistent with a significant glueball admixture than with a pure quark-antiquark interpretation. But the physics community has not declared this a definitive discovery, and there are good reasons for that caution. The systematic uncertainties in partial wave analysis remain substantial. Different fitting strategies can shift the conclusions. The mixing model depends on theoretical assumptions about how the glueball couples to quarks, and these assumptions are not uniquely determined by the data. Alternative explanations, while less natural, have not been definitively excluded. The data are consistent with a glueball interpretation. They favour it, arguably, but they do not compel it with the kind of overwhelming, unambiguous statistical force that the physics community requires for a discovery claim. This is how science should work. The bar for claiming a discovery is high, especially when the claim would be extraordinary, and the discovery of a glueball would be extraordinary. It would be the first confirmed particle in nature whose constituents are entirely force carriers. It would be a landmark validation of quantum chromodynamics in a regime where the theory has never been directly tested in this way. Getting it right matters more than getting it first. There's another angle to the glueball search that has received less public attention, but may prove equally important. So far, we've focused almost entirely on the lightest scalar glueball, the one with zero spin. But lattice calculations predict a whole spectrum of glueball states. The next one up the ladder is the tensor glueball, a state with spin 2, predicted at a mass of roughly 2300 to 2400 megaelectron volts. And the tensor glueball has its own set of candidates and its own set of puzzles. The experimental landscape for tensor mesons, particles with spin 2, is somewhat less crowded than the scalar sector. There are fewer established quark-antiquark states in the relevant mass range, which means less mixing to worry about. In principle, This could make the tensor glueball easier to identify. A new tensor state appearing at roughly the predicted mass, produced strongly in gluon-rich processes, could stand out more cleanly from the background of ordinary mesons. Several tensor meson candidates exist in the mass range where the tensor glueball is predicted. The particles F2 1950 and F2 2340 have both been discussed in the literature as possible states with significant glueball content. But the experimental data in this mass region are thinner than for the scalar sector. Fewer experiments have specifically targeted tensor states in gluon-rich production mechanisms. The statistics are lower. The partial wave analyses are less constrained. As a result, the tensor glueball search lags behind the scalar glueball search in terms of both data quality and theoretical consensus. This is likely to change in the coming years. As BESIII continues to analyze its massive dataset, and as new experiments come online, the tensor sector will receive increasing attention. A confirmed tensor glueball, with its spin-2 quantum numbers, would actually be a cleaner identification in some ways than a scalar glueball, because the mixing with ordinary mesons is expected to be less severe. If the scalar and tensor glueball candidates were both identified consistently, at masses matching the lattice predictions and with production properties matching gluon-rich expectations, the combined evidence would be far more compelling than either candidate alone. Before looking ahead to future experiments, it's worth pausing to appreciate a remarkable development that has unfolded alongside the glueball search, and that gives the broader quest for exotic hadrons an entirely new level of credibility. Over the past 2 decades, physicists have discovered a growing family of particles that don't fit the traditional quark model. Not glueballs, but other exotic states that quantum chromodynamics predicted, but that experimentalists long struggled to find. These discoveries have transformed the landscape, demonstrating that the strong force builds structures far stranger than simple baryons and mesons, and lending powerful circumstantial support to the idea that glueballs too must be out there. The traditional quark model allows only 2 types of hadrons: baryons, made of 3 quarks, and mesons, made of a quark and an antiquark. But quantum chromodynamics, the full theory, allows more. It allows tetraquarks, states containing 2 quarks and 2 antiquarks. It allows pentaquarks, states containing 4 quarks and 1 antiquark. It allows hybrid mesons, states where a quark-antiquark pair is bound with an excited gluon field, contributing actively to the particle's quantum numbers. And it allows glueballs. All of these are permitted by the mathematics. For decades, the only hadrons anyone had confirmed were the traditional baryons and mesons, and the exotic states remained theoretical possibilities without experimental backing. That changed dramatically starting around 2003, when experiments began finding particles that couldn't be explained as ordinary quark-antiquark mesons or 3-quark baryons. The X3872, discovered at the Bell experiment in Japan, was one of the first. It sits at a mass that doesn't match any predicted quark-antiquark state, and its properties suggest it might be a tetraquark, a molecule-like state of 2 quarks and 2 antiquarks, or some other exotic configuration. Since then, dozens of similar states have been found in experiments around the world. The ZC3900, discovered at BESIII in 2013, carries electric charge, which immediately rules out any interpretation as a simple quark-antiquark meson or a glueball. A charged state must contain quarks, and a minimum of 4 quarks is needed to explain its properties. Perhaps the most dramatic exotic discoveries have come from the LHCb experiment at CERN. In 2015, LHCb announced the first evidence for pentaquark candidates, particles containing 4 quarks and 1 antiquark. Then, in 2019, with a much larger dataset, the collaboration resolved the signal into 3 distinct narrow states
called PC4312, PC4440, and PC4457, observed in the decay products of a heavy baryon, with quantum properties consistent with 5 quark configurations. In 2021, LHCb found TCC, a tetraquark candidate containing 2 charm quarks and 2 light antiquarks. This was the first confirmed tetraquark with 2 heavy quarks of the same flavor, a configuration that had been specifically predicted by theory. Why does this matter for glueballs? Because every confirmed exotic hadron is a validation of quantum chromodynamics beyond the simple quark model. Each one demonstrates that the strong force builds structures more complex than 3 quark baryons and quark-antiquark mesons. Each one shows that the mathematical framework of quantum chromodynamics, the framework that predicts glueballs with equal confidence, is correctly describing the full complexity of hadronic physics. If tetraquarks exist, if pentaquarks exist, if the strong force assembles quarks into configurations the simple quark model never anticipated, then the case for glueballs existing becomes harder and harder to dismiss. The same theory, the same equations, the same lattice calculations that correctly predicted the existence of exotic quark states also predict glueballs. You can't accept one set of predictions and reject the other without explaining why the theory would be right about tetraquarks and pentaquarks, but wrong about glueballs. The exotic hadron revolution of the past 2 decades has made the glueball prediction stronger, not by providing direct evidence for glueballs themselves, but by systematically confirming that quantum chromodynamics gets exotic physics right. Looking ahead, there is reason for optimism about resolving the glueball question directly. BESIII is still analyzing data, and future runs may collect even larger datasets. The PANDA experiment at the Facility for Antiproton and Ion Research, known as FAIR, currently under construction in Darmstadt, Germany, is specifically designed to study hadron spectroscopy with antiproton beams. It will produce copious gluon-rich environments through proton-antiproton annihilation, and its detector is optimized for precisely the kind of partial wave analysis that glueball searches require. What makes PANDA particularly promising is that it takes a fundamentally different approach from BESIII. BESIII produces J-psi particles from electron-positron collisions and studies what the J-psi decays into. PANDA will collide antiprotons directly with protons in a fixed target, at tunable energies that can be dialed precisely to the mass range where glueball candidates live. When an antiproton meets a proton, the quark and antiquark content can annihilate directly, converting the collision energy into a gluon-dominated intermediate state that then materializes into hadrons. This is similar in spirit to J-psi radiative decays, but the production mechanism is different, the backgrounds are different, and the systematic uncertainties are different. If PANDA sees the same glueball-like signals that BESIII sees in a completely independent production environment with completely independent detector systematics, that convergence of evidence would be enormously powerful. Conversely, if PANDA sees nothing where BESIII sees a signal, or vice versa, that disagreement would force a fundamental reassessment. PANDA's detector is designed from the ground up for precision hadron spectroscopy. It will have excellent particle identification, high-resolution calorimetry, and tracking precision optimized for the mass range where glueball candidates are expected. Its luminosity, the rate at which it produces collisions, will be high enough to accumulate large datasets relatively quickly. When PANDA begins operating, likely in the late 2030s, it will bring a powerful new tool to bear on this decades-old question. Other experiments continue to contribute as well. The LHCb detector at CERN has begun studying central exclusive production in proton-proton collisions with increasingly sophisticated analyses. Future electron-positron colliders, if approved, could produce J-psi and other heavy quarkonia in quantities that dwarf even BESIII's sample. Each new dataset, each new experiment, each new analysis technique brings the community closer to an answer. Now, let's step back from the technical details and think about what a confirmed glueball discovery would actually mean. Not just for particle physics, but for our understanding of what matter is. We use the word matter every day, without thinking much about what it means. Matter is stuff. It's the substance of things. It's what you're made of, what the Earth is made of, what stars are made of. Matter has weight. It takes up space. You can push it and feel it resist. It seems solid and real and fundamental. And for centuries, the question of what matter is made of at the deepest level has driven physics forward. The answer that emerged over the past century is that matter is made of particles. Quarks and leptons. These are the building blocks. Everything else is assembled from them. Forces are different from matter. Forces act between particles. They push and pull. They carry interactions. But forces themselves are not stuff. They're not substances. You can't hold a force in your hand. You can't weigh a force on a scale. Forces are what matter does, not what matter is. Or so the intuitive picture suggests. The glueball demolishes this intuitive picture. A glueball is a particle, a genuine physical object with mass and energy and momentum that is made entirely from force carriers. It's made from gluons, the particles that carry the strong force. It has mass, not because it contains heavy building blocks, but because the energy of the force field binding itself together has mass through the equivalence of energy and mass. It takes up a finite region of space. It can be produced in collisions, and it decays into other particles. By every operational definition of the word, a glueball is matter. And yet it contains no quarks, no leptons, no traditional building blocks of any kind. It is force that has become matter. This forces us to confront a deep truth about the universe that most people never encounter. The boundary between force and matter is not as sharp as everyday experience suggests. In quantum chromodynamics, forces and matter are not different categories of existence. They're different aspects of the same underlying quantum fields. The gluon field is a force field when it mediates interactions between quarks. It is matter when it binds itself into a glueball. It doesn't change its fundamental nature. The field is the field. What changes is how it's configured. In one configuration, you call it force. In another configuration, you call it matter. But the distinction is in the arrangement, not in the substance. This is actually already true for ordinary protons and neutrons, as we discussed earlier. Over 99% of the proton's mass comes from gluon field energy, not from quark rest masses. The proton is overwhelmingly made of the strong force's energy, dressed up in a thin costume of quark flavors. The glueball simply strips away even that thin costume. It's the strong force with no disguise at all, pure field energy organized into a particle. And this tells us something profound about the nature of mass itself. Mass, in our everyday intuition, is the most solid, most fundamental, most irreducible property of matter. Heavy things are heavy because they contain a lot of stuff. The more stuff, the more mass. But in quantum chromodynamics, mass doesn't work that way. Mass is not proportional to the amount of stuff inside a particle. It's proportional to the amount of energy. And that energy can come from interactions, from motion, from the dynamics of quantum fields, without any underlying stuff at all. A glueball has mass, but it contains no massive ingredients. Its mass is pure dynamics, pure energy, pure interaction. This is Einstein's equation made manifest in the most vivid possible way. Energy is mass, mass is energy, and you don't need matter to have either one. Think about what this means for the universe as a whole. Everything around you,
every solid object, every tangible thing, is overwhelmingly made of interaction energy rather than particle rest mass. The chair you're sitting on feels solid and substantial, but that substance is primarily the energy of quantum fields, particularly the gluon field, configured in specific patterns that create the illusion of solidity. The glueball is the purest expression of this truth, a particle that is nothing but field energy, yet is every bit as real and as measurable as a proton. The history of physics has been a long series of lessons in humility. We learned that Earth is not the center of the solar system. We learned that the solar system is not the center of the galaxy. We learned that the galaxy is not the center of the universe. We learned that matter is not continuous, but made of atoms. We learned that atoms are not indivisible, but made of smaller particles. We learned that particles are not solid objects, but excitations of quantum fields. Each revelation stripped away a layer of intuition, replacing a comfortable picture with a stranger but more accurate one. The glueball, if confirmed, would add another item to this list. It would strip away the comfortable distinction between the actors and the stage, between the things that exist and the forces that act between them. It would show that force carriers can become the things themselves, that the boundary between matter and interaction is not a boundary at all, but a human convenience, a linguistic habit, a way of categorizing phenomena that breaks down when you look closely enough. Quantum chromodynamics predicted this decades ago. The mathematics has been clear since the 1970s, but mathematics is abstract. A confirmed glueball would make it concrete. It would be a particle you can produce, detect, measure, and study. A physical object sitting in your data, made of nothing but gluons. A proof that the universe builds its structures from ingredients far stranger and far more elegant than our intuitions suggest. And this brings us back to where we started. The question in the title: how can a particle be made of pure force? The answer, carefully stated, is this: it can't, if by force you mean something without physical reality, something abstract and immaterial. But a gluon is not abstract. A gluon is a real excitation of a quantum field. It carries energy, momentum, and color charge. It interacts with other gluons through the strongest force in nature, and the energy it carries has mass. When gluons bind to each other, the energy of their binding creates a massive particle, just as the energy of gluon interactions inside a proton creates most of the proton's mass. The glueball is not made of nothing. It's made of the same stuff that already gives you almost all of your weight. It's just made of that stuff without the quarks that usually come along for the ride. The title calls it pure force. The physics calls it a bound state of the gluon field. The truth is somewhere in the poetry between those two descriptions. The strong force is unusual among the forces of nature because its carriers interact with each other. Because gluons carry color charge, they pull on one another with the same ferocity that they use to bind quarks. And that self-interaction, that single property distinguishing the strong force from electromagnetism and from gravity, opens the door to bound states that contain no ordinary matter at all. The mathematics demands these states exist. The experiments have spent decades searching for them. The data, cautiously and with appropriate hedging, are beginning to suggest that at least one has been found. We don't yet have a definitive, universally accepted confirmation. The evidence is suggestive. It favors a glueball interpretation, but it has not yet crossed the threshold that would let the physics community declare, with the kind of confidence reserved for established facts, that glueballs have been discovered beyond all reasonable doubt. That moment may come soon. It may come from BESIII's continuing analysis of its massive J-psi dataset. It may come from Panda when that experiment begins taking data. It may come from an unexpected convergence of results across multiple experiments, each one insufficient on its own, but collectively overwhelming. The history of physics teaches us that nature reveals its secrets on its own schedule, not on ours. But whenever that moment arrives, it will mark something genuinely remarkable. Not just the addition of a new line to the catalogue of known particles, not just the confirmation of a 40-year-old theoretical prediction. It will be a demonstration, written in the language of actual experimental data, that the universe does not draw a hard line between force and matter, that the carriers of the strong force can become particles in their own right, that mass can arise from pure interaction energy with no material building blocks required, that the stuff of the world at the deepest level we can probe is not stuff at all. It's dynamics, it's energy, it's fields interacting with themselves in patterns complex enough to create the illusion of substance. Every atom in your body is already testament to this truth. Your mass is overwhelmingly gluon energy, not quark mass. You are already, in the most literal physical sense, a walking monument to the ability of force to masquerade as matter. The glueball simply makes this truth inescapable by removing the last trace of quark content and showing that the force alone is enough. The universe, it turns out, does not need building blocks to build things. It just needs interactions. And the strong force, with its self-interacting gluons and its absolute refusal to let color-charged objects fly free, has been quietly demonstrating this for as long as matter has existed. We are only now, after decades of theoretical work and painstaking experimental effort, beginning to see it clearly. The next time you pick up a solid object and feel its weight in your hand, remember what you're actually holding. You're holding quantum field energy, organized by the strong force, given mass by the interactions of gluons. You're holding something that is, at its deepest level, not so different from a glue ball.
The only question is whether the universe has also built objects that take this principle all the way to its logical conclusion. Particles, where the force stands completely alone, with no quarks at all. The mathematics says yes. The experiments are closing in, and one day, perhaps soon, we'll know for certain.